Jim has been a serial entrepreneur in fields of programming, machine learning, and medicine, and has volunteered with FLI. Jim's here to talk today about problems in computer security that we might want some focus on in advance in order to build safe testing environments for artificial intelligences that can reason more generally, as quite possibly relevant to Paul's talk as well. So let's so join me in welcoming Jim Babcock today. Thanks.
Thanks, Patrick. Before I launch into slides, I think I'm going to use the whiteboard a little bit. So the previous talk, which we just had, Paul Cristiano, talked about capability decomposition, which is where, because it may be difficult to make a sort of unified reinforcement learning agent that has the properties we want, but we build some sort of structure out of sub-agents, like and these sub-agents do things like some of them communicate with each other, some of them control each other's reward channel, and then at the end, there's an output that goes to the environment, and the environment gives back observations. But you could imagine setting up something like this, and one of the sub-agents notices, let's say this one, notices that this other sub-agent over here has some information that would really help it to get a higher reward. So it tries to find a communication side channel to talk to this one. And this one also notices that this one has some information it would want, and they trade information and suddenly are not following the structure that the developers intended, and it becomes very difficult to reason about. Another thing that could happen is, say this agent sends this agent a malformed observation that changes its behavior to be something different. For example, if this one is giving rewards back to this one, it might send a message that causes it to always give maximum reward, because that would be really great. What I mean by AGI containment, what I'm going to be talking about, is you're setting up a computational environment for all of these sub-agents to interact in. How do you make it so that that setup enforces the constraints and the structure that you intended your system to have, so that agents aren't communicating unless you actually wrote function calls from one to the other, and they aren't randomly giving each other buffer overflows and crazy stuff like that. The extreme case of this going wrong would be if one sub-agent takes over the computational environment entirely, has a network connection, and starts interacting with the internet, where there's all sorts of trouble that it could get up to. But that's one of the easier failure modes to defend against, at least if you're testing, because you can just unplug cables. But when you have parts that are supposed to be interacting, you can't put an air gap between them. Today, AIs are not smart enough to discover computer security vulnerabilities. In general, there's sort of borderline cases that you might call a narrow AI, but would be pushing the definition a little bit. But decades down the line, this may be an issue. The specific vulnerabilities that exist today probably aren't going to exist decades down the line. So I'm going to present some examples to give a feel for what sort of computer security vulnerabilities are possible. But what I'd rather you be thinking about is the shape of the computational environments and how the pieces interact, and what that means for what things need to be hardened and how to put those pieces together. So an example setup, a little more concrete than the thing I drew on the whiteboard. Suppose you have an AI that plays Mario. So it sends buttons one way, it gets back pixels, and then at the end of your test, Mario spits out a performance report, which goes to the developer. It turns out that the Super Nintendo game Super Mario World has a buffer overflow. Human players discovered in this order ways to make the game glitchily produce game objects, a way to make the game glitchily jump to the end of game you win screen, and then a way to make it load a program via the controller port and start playing Snake. That required very precise input. The controller port was not connected to a real controller with human hands. But just in the last month, someone did manage to do it without machine aid, and made Super Mario World transform into Flappy Mario, a Flappy Bird clone, entering the entire program and triggering the memory corruption by hand. And I think live streamed it on YouTube so people could see that he got it on the first try. So in setups like this, the Omohundro thesis about convergent instrumental goals applies. You have sub-agents. Most setups will give them certain incentives. If they have a goal that they're able to optimize, then they'd prefer that AGIs that are similar to them come to exist, because those will optimize similar goals. So, for example, if the AGI could output either everything is great or there is a catastrophic error, if it outputs there is a catastrophic error, then this will cause AGIs like it to not come to exist in the world, because developers won't try that again. But if there's two AGIs with different incentives, then it can report catastrophic errors only so long as they're maintaining those separate utility functions. And all of these instrumental goals, it helps to find security vulnerabilities that let it break constraints that the environment is trying to impose on it. So what do I mean by an AGI container? What I mean is it enforces the structure that you thought you had and makes sure that the computation really has that structure. So it only runs the code that you want in the places that you want. Things don't have unexpected input or output channels. The log files are logging what really happened and not what the AI would want to be in the log files. Tripwires work. You can reproduce it. You can reset it and not find out later that it reprograms the hardware on you. And you can do, and if you have a data center of these things, you can do several tests in parallel and they are properly isolated. So how would it be able to run code that you didn't want or expect? Well, you might give it permission to self-modify, but assuming you didn't do that, it might output an image, and then some other part of it reads that image, or the developer reads that image on their workstation, and image formats are complicated, and libpng occasionally has security vulnerabilities discovered in it, which will execute arbitrary code on whatever computer opens that image. An AI that is modular, if one module sends messages to another that are malformed, then that could trigger a buffer overflow. It could take over that other module, or maybe it breaks more of the constraints than that. One type of output that's particularly a problem. Text is not just text. I don't know how many of you have worked with this particular aspect of Unix and Linux before, but text is a bunch of printable characters and occasionally a command that says something like move the cursor to the left of the line or clear everything below the cursor. And this protocol goes back to the 70s and is really, really messy. The things that interpret it sometimes have buffer overflows. One example in Xterm, you can send an escape sequence that says
your shadows.
Oh, sorry. You can send an escape sequence that says set the window title so that when you alt-tab, you know what's in that window. And then you can send another escape sequence that says echo back what the window title is. And what a program can do is set the window title to command new line, send a echo back the window title sequence, and then quit. And then the window title sequence gets typed into the shell that ran that program. There's also hardware problems. There's a now fairly famous issue where if a program accesses memory in a particular pattern, it causes something like an electrical fault in DRAM chips that will randomly flip bits. And security researchers found that they can exert some control over which bits get flipped and cause permission bits to get flipped in memory page tables. It's kind of ridiculous. And that's now basically fixed on most computers by tweaking some electrical parameters of how often the RAM gets refreshed. But there are probably more problems like this waiting to be found. So, should only execute the code you think it's running. Should not get information from places you don't think it's going to get it, or send information where it shouldn't. Another famous named security vulnerability was called GSMEM. And the way that works is someone puts a reprogrammed cell phone on top of a computer's case, and a program running on that computer accesses memory in a way that generates radio frequency interference and sends a message to the phone. So, militaries and organizations that like to be careful with their secrets will put glue in all of the USB ports and not provide any network cables or anything. So obviously you couldn't get any information out except by laboriously typing it into that phone by hand, right? If a program has access to a clock, and the same computer is also doing AES encryption operations repeatedly, then by measuring cache timings, the program can extract information about the AES secret key.
I'm sorry, you began to talk with saying vulnerabilities are not magic.
So,
Shadow, can we move this back to where it was before Paul talked? And then it might help.
So, it seems kind of like magic if you don't know what the space of possibilities that these things are working with is. But if you draw a diagram of all of the parts in the CPU, you can see, yeah, these two processors are sharing an L2 cache, and that means that they will occasionally affect each other's timing. And if you are really, really careful about it, you might try to prove that they don't, which would probably mean just putting them on separate CPUs, because that's easier. Log files, debug information. So I'm envisioning this as an AGI has some print statements in it that occasionally print out details about what it's doing that the developers will look at later. If it's running the code you think it is, this is mostly fine. If it's not running the code you think it is, then that could be anything, including weird X-term escape sequences. And as far as debugging, there's two general categories of debuggers that exist. There's the usual kind of debugger, which assumes that you're debugging a program that you wrote, you have its source code, and it isn't malicious. If you attach your normal Python debugger or GDB to a malicious program, then it might take over the debugger. This isn't a failure mode that people are particularly worried about because people don't use debuggers in that sort of circumstance. But there's a different kind of debugger, which is intended for debugging malware. But which generally assumes that you're working with assembly, because malware doesn't give source code. So one thing that I think people should be doing is making a middle category of debuggers that is hardened but designed for cases where you really do have the source code and have at least presumptive assumptions about what you're looking at. Tripwires. So one example of a tripwire is this sort of stylized assert statement, assert not taking over the world. We can't really design things like that today because we don't know what the algorithms are going to be. Paul had some ideas about guaranteeing non-catastrophic execution that depends on a particular setup. But what I'm more interested in, which we can work on now, is technical tripwires that assert things like this data structure is not corrupt. There aren't pointers pointing to weird places, or pointers that are null that shouldn't be, or cycles in your data structures, things like that. The thing that is kind of tricky about that is if an AGI is reflective, it can look at this Venn diagram and try to aim at this slice. So an interesting software architecture problem is how do you allow introspection while denying access to that information? Have a program that can look at everything about its source code except for where the assert statements are and what they say. How am I for time? So reproducibility. It's a bunch of issues. If you write a fully deterministic program, then in principle it's reproducible, as long as by the time you're investigating what went wrong, you still have the pseudo-random seed. You still have all of the inputs. You haven't lost track of things. So some programs look deterministic but aren't because of race conditions. For example, you write a program that's multi-threaded, and it has slightly different behavior based on which of two things finished first. Pure functional languages like Haskell, I think, let you get guarantees of this not happening. Something like Python, that won't happen. So there's a programming languages research question, which is how to get guarantees of no race conditions. Secure resets. So yo dog, I heard you like computers, so I put 10 computers inside your computer. Each component of a computer typically is another computer that you don't really think about, because all it's doing is managing the interaction between itself and the main computer. But security researchers do think about these things and sometimes find ways to reprogram them to make it so that when they take over a computer, it is persistent, so that if the user reinstalls the operating system, there's still malware there. So Jellyfish is a bit of malware that runs on GPUs. That is a research project on GitHub. It lives in memory, so if the computer is powered down and turned back on, it will go away. But if you just hit the reset switch, it'll stay. The NSA had a catalog of all of their computer security tricks leaked a few years ago, and it contains lots of things like, for example, Irate Monk, which programs not the hard disk contents, but the controller that decides where on the hard disk to read next to order reads and writes for good performance, and makes it so that if it's reading an executable off the disk every 1000th time or something, it will read a different executable that contains their code. So test isolation, you don't want experiments communicating with each other if they weren't supposed to. You don't want one test changing the hardware and affecting all the subsequent tests. Similar sorts of vulnerabilities are a problem. So there's all these technical issues, and then there's also humans. So In the early days of Less Wrong, Eliezer Yudkowsky ran what he called the AI box experiment, where he would have an IRC chat lasting a few hours with someone role-playing as a gatekeeper, and try to convince them to let him out of the box. And he didn't succeed every time, but he did succeed. And the superintelligence is probably smarter than any humans, so it should be able to do this as well. And so other people reproduced it. Tuxtidge was another user who ran AI box experiments and succeeded at them. But you can't persuade a human to do something without actually being able to talk to them. So there's a policy question, which is if the AGI outputs things, what outputs are okay to read, and who is it okay to read them? And that depends how smart you think it is, on how much you trust the specific people involved, on what that output was for, and how you think it's optimized. The container's job is to enforce that policy, to make sure that a developer can read log files while a passerby can't receive text messages telling them that it would be fun to plug in extra network cables. So if you're really, really, really paranoid, then you can use some fairly extreme strategies, like have the AGI's output only be the answer to one multiple choice question. And A, B, C, or D, none of these answers is going to trick me into pasting the AI's source code onto a different server. There's just not enough information there. A similar thing, which can solve problems like rowhammer with high reliability, is homomorphic encryption, which transforms a computation into something that is much slower, but doesn't interact with the hardware in any way that's distinguishable from randomness without access to a particular cryptographic key. So in the paper about this, we define a hierarchy of degrees of caution, essentially, from light containment for, well, we don't really have a working AGI yet, but we'll use some software as long as it doesn't get in the way, which I think of that as if we can write software for containment, and some measures will just be drop in, doesn't cause any problems for the developers, just makes things silently more reliable, instead of all of those things. And then there's some more things you could do to make it more reliable that slow things down or make the developers do extra work. And those are medium containment. And then there's some things that slow things down a lot and lessen the AI's capability. And I think we call those heavy containment. So that's an overview of the problem.
Are you going to give us the solution, or is that the end of the talk?
That is not the end of the talk. I'm going to tell you about off-the-shelf technologies that are partial solutions, and say that we need more research to make these better.
Actually, I have a question.
Yes.
So, like, with the problem, it kind of, you had this slide saying all of your invariances, and you had this, list of invariances.
Yes.
That you kind of want. I'm wondering, how do I generate a list of these invariances such that, I'm sure that I haven't missed one, that, if I had thought more, I would say, oh, I actually want this for the property. Or is that just like not reasonable to expect?
I don't think the list is complete.
Okay.
I'm sure that there are more things, and specific projects will have specific invariants as well about like their data structures and amount of computation that pieces use, and I'm sure many other things that I haven't really thought about. The strategy that I used to generate that list was thinking about what properties, if they failed to hold, would break everything else so that you couldn't possibly have any other invariants besides those.
Okay.
Other questions before I go on? So here's sort of an overall picture. So conceptually, you have an AGI program, and it's written in some programming language, and that programming language is a sort of sandbox. A few programming languages actually call it that, like the Java sandbox. The basic premise is, well, if you never mention the functions that make network connections, then clearly this program is not going to make network connections. You hope. I mentioned a few loopholes and that sort of thing. But it's a partial solution. It's clearly much harder for, it's clearly a significant obstacle to break out of the language model for a program. If it's going to corrupt its own memory, it's very likely to crash itself instead of doing the particular weird thing it wanted. Then there's the operating system privilege model, where when you run a program, you can say this program is only allowed to access these particular things and nothing else. Linux has a version of this, BSD has another version of this, Windows has another version of this. The defaults are pretty permissive, but if you put in the effort to say exactly what it's supposed to be able to access, then the operating system will enforce some things for you. But the Linux kernel occasionally has security vulnerabilities as well. So you've got that, and then also you have a virtual machine. A virtual machine is like an operating system inside of an operating system, where you have the Linux kernel, and then that runs a program which emulates another computer using the similar hardware so that it's fast emulation. And then that computer has another kernel, and then that runs a program that is the AGI. And then the fourth layer on top of that is you keep track of what wires are connected to what. And the idea is that these are conceptually dissimilar enough that if you find a security vulnerability in one, it doesn't really help you very much with finding security vulnerabilities in the other ones. So this diagram, say the AGI starts down here. If it has permission to self-modify, then it can follow this arrow and get up to here. And if it finds a vulnerability in its debugger, then it can get up to here. And if it finds a bug in its in the driver that controls the GPU, then it can get up to here, and so on. It has to get all the way up to here before it can actually interact with the internet. And as it goes up, properties that you would want it to have stop holding. And the idea is you build a multi-layer thing like this, and then in each layer there is some monitoring that looks at the inner layers and checks that they are only running the code that they're supposed to be running. So language semantics. I just talked about that. On a scale, there's a scale running from C to Haskell, where C is almost impossible to write correct programs in, and errors lead to amazingly complete controllability to Haskell, which has a very thorough, strict type system, which doesn't really have this sort of problem. The problem is that a program written in Haskell is still dependent on a bunch of software libraries for doing things like interact with the GPU and I/O and loading data, and those might be written in C with problems in them. So next layer, operating system sandboxing. There's at least a couple dozen of these. One in particular, just to give you a sense of how they work. Linux has a mechanism called seccomp, where the program starts running, it initializes, it opens all of the files it plans to use, and then it says, from this moment forth, I will never open another file. I will never make another system call except to interact with this set of files that I already have open. And if I ever break this promise, then send me sigkill. That's the default, and a more refined version that Linux also supports is to say, all of the system calls I will make from now on, if you feed them into this short little program, will return 1. That program is called the Berkeley Packet Filter. It was originally designed for network firewalls and got repurposed for this. Virtual machines. There's about 1 security vulnerability per major virtual machine product per year that would allow breaking out of the virtual machine sandbox. Hopefully a decade from now, they'll all be found and there won't be any left. We can hope. Maybe we can speed that up.
Or maybe there can be a formally verified virtual machine.
We can hope. Virtual machines have a fairly complicated surface area because they're not just providing a CPU for programs to run on, they're also providing a virtualized video card.
It doesn't necessarily have to, right?
If you want it to run an AGI, it probably does have to. So GPUs are these incredibly complicated things, and they have these drivers that essentially take code that you wrote for the GPU and compile it. And in a virtual machine, that driver lives on the host system instead of on the guest. Both NVIDIA and AMD have projects in the works to try to change this, but they're not done yet. For now, this is what you get if you use a GPU. This is a quote I found out on a random internet forum from a former developer at NVIDIA about how complicated GPU drivers are. And apparently, GPU vendors and video game companies have been working around each other's bugs for more than a decade. And the result is that they are extraordinarily complicated. They're also full of bugs. They're written in C++, and they run with very strong privileges. So this is a problem. Google recently announced their tensor processing units, which sound kind of like their non-backwards compatible machine learning only GPUs. And I think that's great because it means they don't have to use this million-line driver code base to run their AIs. So network topology, you can air gap your system. This is what people used to think about when talking about AI boxing. You just put it in a concrete shell or something and don't have any network cables in, and yeah, that means that it's not going to interact with the outside world in any ways you didn't intend. But that's totally useless because you do actually want to use it. You want to test it. You want parts of it to test each other. And also, developers like to work in nice offices, not in isolated concrete bunkers. So what I expect to happen is that these will be configured with routers that limit what can talk to what, which might have vulnerabilities in them, hopefully not. But no actual air gapping. So, questions about any of this? Okay, so I have one more slide, which is what can we do about it today? The nice thing about this is that it's a bunch of work that calls for a completely different skill set than the usual AI safety work, so different people can work on it. Making a hardened debugger does not require any knowledge at all about machine learning. And machine learning does not require any knowledge at all about the software architecture of debuggers. So this is something that can be pretty costlessly pursued in parallel. Not costlessly because of how society is organized, but in principle could be done costlessly in parallel. It would be very valuable if someone were to set up red team events where there's a setup that represents an AI container as it would normally, as one might expect to be organized, and people compete to break out of it or to break its invariants and then report how they did it. This is how the world of computer security has gotten successes elsewhere. For example, every year there is a contest to break out of the Google Chrome sandbox for $60,000. I believe that prize has been claimed every year, but every year the way that it's done gets more impressive. So that's where we're at as far as the infrastructure that I see AI is being built on, and changes that I think need to be made to make them more secure.
Thank you. have time for a bunch of questions, for like 3 or 4 questions.
Okay.
What are your like intuitions on whether like defense can overpower offense, so to speak?
In the broader world of the internet, where people are running lots and lots of different programs, not necessarily investing at all in security, offense pretty reliably wins over defense. At least it has so far. I don't expect that to change. In the context of an AI where the developers can invest in making things secure, I think it could go either way, and there's a reasonable prospect that defense will win. And even if it's not possible to get rid of all the security vulnerabilities, just because there's a vulnerability doesn't mean the AI is going to be smart enough to find it.
So I'm surprised you didn't mention formal verification and type theory as part of this, because it seems like projects like a version of Linux that is formally verified goes a long way towards hardening not just the attack vectors that you know about, but ones you don't yet know about.
Yeah, so I bundle that in language semantics. There's an isomorphism between type checking and formal proofs. They're not exactly equally expressive, but if you have a sound type system like in Haskell or Rust, for example, then there is implied in that a proof that certain kinds of errors aren't present.
Probably want to go a step further to sound-dependent type system, something like AGI, where you can like express computations with types like in Haskell, but like the types are expressive enough that you can actually prove quite complicated things.
I agree, but I also think that replacing all the legacy C code with anything else is a much bigger gain than going from reasonable programming languages to the very best possible programming languages.
Oh. Yeah, related to Svi's question, what are your intuitions about bugs currently being dense versus sparse, and what is possible to make by using different architectures? Are you familiar with the vocabulary? Like dense kind of means that like no matter how many bugs we fix, someone will be able to find another one and another to exploit.
So there was a recent advance in bug hunting techniques in the form of a program called AFL Fuzz, which revealed that the bugs were denser than everyone had thought. There were a lot of old programs that had gotten a lot of attention, a lot of bug fixing, and people thought that they had probably gotten everything or almost everything, and then they hooked it up to this really sophisticated fuzzer that generates random inputs in a strategic sort of way, and it finds huge numbers of vulnerabilities in them. And that still doesn't cover all of the types of bugs. In particular, we know that it doesn't cover bugs. We know for sure that it can't find bugs that require very large inputs or triggering certain kinds of integer overflow.
So when I'm thinking about things like this, like one of the main things that seems like especially hard to defend against is steganography. Is like if there's any channel from the AI communicating with humans who eventually like do things to the internet, any kind of information theoretic channel of that form that has like more than some number of kilobytes,
right?
Then it seems easy to like create a message, encrypt it with a lead key, and then put it on the internet. Eventually, someone figures it out.
Right. So the problem there is that you could ask the AI to paint you a picture, and this picture is nice, so you put it in your press release, and later it turns out it contained the AI's source code.
I think that the main thing I'm uncertain about is like if we had a way to deal with this especially difficult problem, would that method of solving that problem also solve like a lot of the other things, or like is there actually a need for different kinds of solutions and different problems?
So there is a possible research path there where people could look into how to take images and noise them and put them through autoencoders and jitter them and whatnot in such a way that steganography can't get through. But the only surefire solution is just never publish that image or anything produced directly by the AI.
Have no information here dependency between the AI and like the internet.
Yes.
Seems like a tall order, but I guess I would prevent that.
Do you envision like also protecting against AIs that can not only write code and like reason about vulnerabilities, but like reason about multiple copies of themselves and similar agents and so forth? That they might kind of like deduce that there is another copy of me running on that server over there, and so coordinate without actually exchanging any information?
There's a lot to think about there. It's definitely worth researching, but it's not something that the software can help with.
Yeah, but it kind of like makes sense to be aware of those kinds of like problems as well, because it kind of might indicate which layers are worse defended than we would think if we were not thinking of those things.
I agree.
All right. So let's thank Jim again.